A mixing vat holds 300 liters of pure water, so pure water, water with nothing in it. A solution of rubbing alcohol containing 4 grams of isopropyl alcohol per liter, one would assume per liter of water, is pumped into the vat at a rate of 15 liters per minute. Starting to get a lot of numbers here as we read. We don't want to get overwhelmed, so we might start drawing a picture. Okay? We've got a mixing vat. I mean, literally the first 3 words were a mixing vat. So the volume here, 300 liters. And then we've got stuff pumped into the vat. So I usually draw a little arrow like this. And so this is our rubbing alcohol solution. It's pure isopropyl alcohol being dissolved in water. And so we've got a concentration coming in 4 grams per liter. And that's coming in at 15 liters per minute. Okay, so that's the flow rate in. That's the concentration of what's being pumped in. At the same time, the well-mixed solution in the vat, so we've got sort of a little mixing, spinning turbine in here, mixing all this stuff up amongst the water. The well-mixed solution is pumped out. So stuff's coming out of the vat at the same rate, 15 liters per minute. That means that the volume overall is not going to change. It's going to be the same amount of water because every minute 15 liters comes in, every minute 15 liters comes out. So it'll stay balanced. We're not filling up or draining this mixing vat. Okay, so we're pumping out at 15 liters per minute. But we don't have a concentration out because the concentration is going to vary over time as we slowly get more and more isopropyl alcohol inside the vat. But we'll talk about that concentration in just a moment. Okay, if M of T represents the mass of isopropyl alcohol, how much there actually is, not the concentration or anything like that, that is present in the mixing vat after T minutes, find an expression for M of T. Okay, so we're going to, as is pretty common for mixing vat questions, set up a differential equation with this given information and solve for M of T. Okay, so the mass of isopropyl alcohol, I'll move over to a fresh sheet of paper in a moment. Let's just talk through it for a moment. The mass is going to change. How is it going to change? Well, some mass is going to come in, and some mass is going to come out. Okay. Well, how much is coming in? Well, 4 grams per liter with 15 liters per minute, that's going to be a total of, I'll write the actual numbers when we move to the separate sheet of paper. But how do we calculate how much is coming in? Concentration in times flow rate in. How about what's coming out? Well, we know it's coming out at 15 liters per minute, but the concentration, well, it sort of depends on how much isopropyl alcohol is already in here, and that's where we get the M of T again. So this isn't just going to be a derivative is equal to some constant. The function refers or relates back to itself, makes it a more interesting differential equation. So it's the mass, but this isn't a concentration. Right? This is not a concentration. Concentrations are grams per liter. You can see this. Now, you don't have to do this, especially if it's just like a math question to you. But if you include units, you'd see pretty quickly there's nothing to cancel out my liters here. So you need a volume. So concentration, you want it to be a concentration, divide by the 300 liters in volume that we have. How much mass divided by the volume of what we're dissolving in, which in this case is water. Okay? So there we've got grams per liter. The liters will cancel out, and then we'll have grams per minute for everything. Units will match. Everything makes sense. It's good to do this sort of dimensional analysis to make sure you have set an equation up correctly. It's a small little thing, and especially, as I say, if you're more of a mathematician than you are, physics or engineering or chemistry or something like that, you're not going to be as concerned with units. In math, we don't care as much, well, at least not in pure math, as much about units. Care a little bit. Sometimes you got to do conversions, but I know me, I focus more on the numbers, but if I keep the units in, I can see, okay, this isn't M of T times 15 because it's not a concentration, it's a mass. And those are different things. They got different units. So, okay, let's start here. Okay, so 4 times 15, it's going to be 60 grams per minute coming in. Okay. And then M over 300 times 15. Well, let's see. 300 is 2 times 150. 150 is 10 times 15. So I can cancel those out, and we can actually turn this into 60 grams per minute minus M over 20 grams per minute. Okay? So that is our differential equation. There is a little bit more information. You may have missed it right at the start because it doesn't have a number. but we're told we have pure water, which means at the very start of all of this, we have no isopropyl alcohol. So we do have an initial condition. Otherwise, we don't have enough information. We'd have a constant. We get a general solution. We wouldn't be able to solve this DE for the particular setup that we have here. So we'll remember that. We don't need it right now. Okay. So what can we do here? Well, this is, well, let's get rid of the units now. They've served their purpose. So 60 minus m over 20. Okay. This is our differential equation for dm by dt. This is separable. It's linear. You can use either one. I'm a big fan of linear for this sort of a thing, so I would rearrange it. But if you want to use, treat it like a separable differential equation, go for it. Absolutely go for it. So I'll write it in standard form. Okay. And say, okay, now I need, so this is linear. All right, make a note of that. It's linear. Yay. And now we need an integrating factor. Well, now that we've got the plus here, we can get an integrating factor. Well, you know, while we're saying things, let's say, hey, we've got an integrating factor. Okay. It'll be e to some antiderivative of 1 over 20. So that'll be e to the t over 20. Great. Now we could do what do the whole process, multiply everything by e to the t over 20 on both sides, and realize that the left-hand side is what you get out of the product rule. I'm just going to go ahead and jump to the formula. I will sort of write it out a little bit here. So if we've got dm by dt plus p of t, which in this case is 1 over 20, q over t, then the formula is you do q over t, integrating factor, so that'll be t over 20 here. No, I have the t over 20, yeah. I was thinking the t was a 1 and I need another t up there, divided by your integrating factor. Okay, in this case, q of t, the constant, the function over here is just this constant 60, so I can go ahead and also bring that in here. So we get a nice little 60 here. Okay. What do I have to do? I just have to integrate now. Okay. You can bring the 60 out, e to the t over 20. Now, if you're experienced with integration, this is actually a really common setup. E to some number, let's call it k. Antiderivative is that. E to the kt goes to e to the kt over k. So we'll have 60, don't forget that 60, e to the t over 20 divided by, let's not forget our plus c, but divided by the k, the 1 over 20. Don't think it's just the 20, otherwise, 60 over 20, you'll think it's a 3, and you won't even bat an eye at it. Plus c over e t over 20. So dividing by 1 over 20 is the same as multiplying by 20, so it's going to be 1200. Okay. And we'll have 1200 e to the t over 20 plus c over e to the t over 20. We can cancel these out a little bit, but you should split up the fraction first. So you'll have 1200 and then c over e t over 20, or I prefer to write it all on one line, e to the minus t over 20. Okay, so there it is. There's our mass function, or at least my general solution for the mass function. We've got this c in here. How can I figure it out? Well, remember, we started with pure water, 300 liters of pure water, so we know if I plug in 0, I should get a 0 out. Well, e to the 0 is just 1, so we got 1200 plus c is 0. C here should be minus 1200. And so we can get our solution. 1200 minus 1200 e to the minus t over 20. That is our solution with all our work shown, initial condition used. This will model the amount in grams of isopropyl alcohol that we would find in this mix. If we drained it of all the water or evaporated, although I think maybe the alcohol might evaporate before the water, in which case that wouldn't work, although maybe if we evaporated and collected the alcohol. But this is how we would model the mass that we would have after t minutes of starting pumping in the solution.